Welcome to the NHP webinar program. Today we'll be taking a look at IP ratings in a practical way. Some of the learning outcomes will be around IP ratings and their definitions and designations. We'll understand how enclosures are tested, along with the expected outcomes and performance expectations. We'll discuss how this pans out in practical terms and examine some tips for applications and some good practice rules. So what is an IP rating? IP stands for International Protection, and it's the identification and classification system to identify enclosure ingress protection according to the tests carried out to comply with AS/NZS 60529-2014. IP is often referred to as ingress protection or internal protection. The standard tests and evaluates an enclosure's immunity to ingress of moisture, ingress of solid objects, and dust particles, as well as immunity to contact of hazardous parts. Due to the potential complexity of this subject, we'll only cover basics and as a consequence will not cover impact durability. This may be covered in future technical webinars on the subject. Enclosures come in many shapes and sizes, both in generic forms and also for specific purposes. They can be made from a large range of materials chosen for suitability to withstand many ambient conditions. The type of enclosure suitable for any given application is generally by agreement between the installer or the supplier and the end user. The most suitable IP rating is commonly chosen by installers as it should be appropriate to house their equipment to ensure security and longevity of the components. Unfortunately, the vast majority know very little about the actual performance and only what is perceived. This is true not only regarding the choice of the enclosure construction materials, but also the appropriate IP rating for the application. Hopefully today we can clarify the IP code and show some ways of determining the most appropriate rating for the job. The IP code designations are fairly simple to understand, roughly what protection factors we can come to expect from an enclosure or for any specification. IP, of course, tells us what we're looking at. International Protection Rating. The first digit determines the protection against solids, from the back of a hand to a minute dust particle. The second digit specifies protection against ingress of water. The third digit is not used much. This digit indicates if any hazardous parts within the enclosure may be touched by a probe device specific to each designation of the first numeral for the solid objects. There are additional letters that may indicate suitability for a specific purpose or application. These are rarely used. The code designations for solid particles seems fairly straightforward. X in the first box means that there is no available test data or there has been no official test. 0 in the box means it has been tested, however it offered no protection against contact or ingress of any objects. 1 says objects greater than 50 mm are prevented from entering. In practical terms, we're talking about the back of an adult's hand. The actual test uses a rigid sphere of 50 mm and allows some entry, however, must maintain clearance, as in the example we'll show shortly. 2 says objects greater than 12.5 mm shall not penetrate. So for numeral 1, the 50 mm rigid test sphere shall not fully penetrate the enclosure opening and maintain sufficient clearance from the potentially hazardous objects to attain the optional third letter A. For numeral 2, a jointed test finger may penetrate to its 80 mm length, but must stop at the stop face. There is a 50 mm by 20 mm section on the back of that jointed finger, and it should not pass through the opening. The joints of the test finger are successively bent through up to a 90-degree angle and must maintain clearance from potentially hazardous objects. This will attain the third letter B. These tests also ensure that the enclosure walls will have sufficient rigidity and resistance not to fail against pressure from an object. The number 3 only allows solid objects under 2.5 mm to penetrate. It protects against penetration by a simple tool such as a screwdriver. Number 4 allows a rigid object under 1 mm to penetrate, as do numerals 5 and 6. However, the test of 5 and 6 becomes rather irrelevant, and we'll see why in a moment. For the optional third letter of C, numeral 3, a 2.5 by 100 mm long rigid test rod may fully penetrate the enclosure opening, however shall have clearance from all other internal objects when rotated in all directions as per the diagram in the middle on the bottom. For numeral 4, 5 and 6, 1 mm by 100 mm test rod is used in the same manner for the optional third letter D in this respect. The access probe test applies to numerals 5 and 6 as well. However, the following tests make the probe fairly irrelevant when we look at the test performed for compliance inside a dust chamber. So numeral 5 and numeral 6, we give them a talcum powder test. The talcum powder test is divided into two methodologies, Category 1 and Category 2. So the Category 1 test is always carried out whilst testing for numeral 6. The test may be carried out for Category 5, however this is optional. The application without differential pressure is Category 2. This is normally carried out for numeral 5. The application of the enclosure where temperature differential may cause a vacuum inside the enclosure, causing powder to be sucked into the enclosure upon cooling down cycle, is very important. Category 1 testing applies the vacuum to the enclosure during the talcum powder test. For Category 2, it's not necessary to have a vacuum. We see here the test for Category 1. The test specimen is inside the enclosure. The talcum powder is circulated through the enclosure. Talcum powder has particle size of 0.075 millimetres. It's held in suspension inside a dust chamber. Talcum powder is continually circulated for a period of 2 hours. The first numeral 6 enclosures are deemed to be Category 1. You can see on the right-hand side of the dust chamber is the vacuum setup. So we maintain a vacuum within the test specimen for that 2 hours, and the Category 1 specimen is deemed to be dust tight. No talcum powder is allowed to enter the test specimen. For the Category 2 test, there is no pressure or no vacuum pressure within the test specimen. The talcum powder dust is circulated throughout the dust chamber for a period of 8 hours continuously. This is a larger enclosure inside the dust chamber following the IP6X test. Many enclosure companies perform these tests in-house and deem the enclosures to attain a certain IP rating. Certified ratings are only obtained when tested with a certified standards test supervisor or in the test facilities. So, if in numeral 6 the enclosure shall be deemed to be Category 1, whether reductions in pressure below the atmospheric pressure are present or not in the application. The protection is satisfactory if no deposits of dust is observable inside the enclosure at the end of the test. Numeral 6, Category 1, is classed as dust tight. Numeral 5, the protection is satisfactory if talcum powder has not accumulated in a quantity or location, as with any other kind of dust, it could interfere with the correct operation of the equipment or impair its safety. Except for special cases to be clearly specified in the relevant product standard, no dust shall deposit where it could lead to tracking along the creepage distances. In these instances, the enclosure needs to be set up with specific equipment that is to be used within that enclosure for the application. Let's have a look at IP code designations for liquids. As with the test for the first numeral, testing for water ingress and the methodology is very specific. The details of the test, while important in their application to determine conformity, need to be understood in a broader sense to understand their suitability for any particular application. Numeral X, no test data is available, no rating is possible. Numeral 0, no test is required if claimed. Numeral 1 and numeral 2 share a similar test. Numeral 1 test with a uniform dripping water vertically for 10 minutes, equal to 1 millimetre of rainfall per minute. With numeral 2, the specimen is placed on a 15-degree angle and rotated on a support 4 by 90-degree increments. It's held in each of those positions for 2.5 minutes, and the equivalent of 3 millimetres of rainfall per minute is dropped from the test box chamber above. Numerals 3 and 4 are again basically the same test with the difference in the angle of the directed spray from an oscillating tube. This oscillating tube can be used or a spray nozzle can be used. So it's either or, both of these tests. The difference between the two is basically the direction of the spray. For number 3, the direction of the spray is between 0 and 60 degrees from the vertical. And for numeral 4, it's between 0 and 180 degrees from the vertical. Another difference is volume of water differs and is more severe at 10 litres a minute for figure 4. Figures 5 and 6 are basically the same test with a variation in water jet volume and obviously the delivery rate. This starts to see a rather noticeable difference in the external forces applied to the enclosure surfaces. The greater volume and delivery of water in the jet causes a higher material distortion to the enclosure surface and seals. The test duration is for 1 minute per square metre of enclosure surface area, or a minimum of 3 minutes for any test subject. The nozzle is very specific in its design for each application. For numeral 5, 6.3 millimetre diameter nozzle outlet is used. The water volume is 12.5 litres per minute for a minimum of 3 minutes from all directions. For numeral 6, 12.5 millimetre diameter nozzle is used. The water volume is 100 litres per minute for at least 3 minutes from all directions. Both have a distance of between 2.5 and 3 metres from the enclosure. We see the IPX6 water test spraying at a distance of 3 metres with the enclosure on a turntable. The enclosure is open for inspection after 3 minutes, plus dripping time, to reveal 0 water deposits. In many outdoor applications where water inundation is over days or weeks, rain hoods are often required to prevent water laying on gaskets for long periods. Some enclosures for this purpose are manufactured incorporating a watershed roof structure. Here is an example of pre-certification tests done in-house. IP testing and certification can be very expensive, so the enclosures are given the treatment in-house before being submitted for the appropriate IP certification. Notice the huge volumes and high pressure of the water. Numeral 7 is compliance for immersion in water for 30 minutes. Must be 150 millimetres below the surface and 1 metre above the bottom of the water tank. These measurements obviously compensate for the difference in pressure on larger enclosures. The deeper the bottoms must go into the water tank. So the test is made by completely immersing the enclosure in water in its service position as specified by the manufacturer so that conditions are satisfied. The position of the enclosure in the water is specified for each dimension of the enclosure to ensure uniform results from different pressure differentials in the tank. The duration of the test is at least 30 minutes. The water temperature must not differ from that of the equipment coming from an ambient air environment by more than 5 degrees. This requirement can be modified if it is established that there will be equipment inside the enclosure operating during submersion. This will mean that there's possibly some temperature differential and therefore pressure differential in the enclosure that needs to be taken into consideration. Numeral 8 is an interesting test as the parameters must be more severe than for numeral 7, but shall be subject to an agreement between the manufacturer and the end user. It should take into account that the enclosure will be continually immersed in actual use. The acceptance conditions allow for water to enter the enclosure, however, not in sufficient quantities or locations to impair safety or interfere with the correct operation of the equipment. Water shall not be deposited on insulation parts or impinge on areas that are creepage zones designed to prevent tracking when under power. It shall not reach live parts or windings that are not designed to operate when wet. It should not accumulate near cable ends or enter the cable. If the enclosure has drain holes, then it must drain away. The IEC 60529 classification IPX9K is now commonly referred to and requested in the food and beverage industry in Australia and New Zealand. It specifies testing with high pressure water jets at and above 80 degrees C, high pressures and very close range. This test classification ensures no ingress under high pressure, close proximity and rapid changes in temperature. The designation IP69K reflects zero dust, zero water under rigorous conditions that ensure the enclosures are fit for purpose in these aspects in the food and beverage industries. Now, dual ratings may be given where the enclosure is of such construction and quality that it can endure high pressure water jets as well as temporary or continuous immersion. These are classed as versatile use for a wide range of applications. They take into account uniform pressure from constant immersion, as well as water jet variable force points from high pressure hose nozzles and variations in internal pressures. So which is the best IP rating? We don't have time to cover all the contingencies here, so let's look at some of the most common in our industry. So let's look at the application it has to be used in. Is it an electrical or electronic application? If so, the devices will have some watts loss when operating, however, at other times none. Now, watts loss can cause heat buildup that may or may not be a lot of increase above the external ambient. Increases in heat cause two major issues. Possible increase in pressure in the enclosure if there's a high IP rating for submersion, and of course the ability to hold more moisture suspended in the air. An increase in air pressure inside the enclosure and its differential compared to the external barometric pressure can cause suck and blow in the enclosure. This cyclic phenomenon can cause moist air from a warmer external ambient to be drawn into the enclosure during latent periods, and this may cause condensation in the enclosure over time. The higher the IP rating, such as IP67, the greater the possible effects on moisture retention. Our industry causes us to house all types of equipment in a myriad of environments. Power electrical devices for simple power distribution, motor starting and control devices, electronic devices, etc. Each can cause their own issues that affect the enclosure's performance, and each requires its own protection factors to avoid malfunction. For instance, electronic devices require excellent dust exclusion as well as restricted moisture ingress. Motor starters can cause thermal cycling because of their starting and operational duties, as well as considerations for vibration from contactor operation. There's also the consideration of differences in supply and field cables and the need to properly gland the conductors to maintain the desired IP rating. The use of hand control devices and signalling or operator interfaces may also have a bearing on the suitability of the enclosure for the purpose. So drilling holes and cutting apertures to house the devices may cause problems with the IP rating. The size of the enclosure can sometimes have ramifications on the expected outcomes. The larger the enclosure, the more difficult it is to maintain the proper sealing for the original rating. Generally, the larger the enclosure, the more cable entries, the greater proportion expansion due to ambient conditions, and the greater possibility of compromising the gaskets and seals. There's also the issue of mounting needs. If the mounting surface is not perfectly flat, the enclosure may distort and breach the seals. Enclosure access varies from application to application. Smaller enclosures have removable lids or covers. Larger enclosures may have hinged doors, some with double doors. Each has its own unique problems. Removable lids sometimes means potential damage to gaskets, including foreign materials attaching themselves to the gaskets. Hinged doors left unrestrained when open may swing in the breeze and contact other items that can cause damage and distortion to the profile, seals and surfaces. Gland plates that are overpopulated, undersized or underdimensioned in thickness, for instance, may also distort, causing breaches in the gland seals. Does the operation of the equipment cause a high temperature inside the enclosure? Then there is outside. Higher internal temperature causes rise in the pressure that leaks out to the atmosphere. As the equipment reduces current draw, it cools down, reducing internal pressure and possibly drawing external air in. As the air cools during the evening, it may cause condensation on the inside of the enclosure, and this can accumulate as the internal temperature in the air exchange never gets to a point to expel all of the moisture. This can cause pooling and corrosion of metallic switchgear components over time. Even when switchgear is not operating, things like solar radiation directly hitting the enclosure can cause larger temperature differentials and cause issues on high IP rated boxes. Understanding these environmental conditions can also be very important, especially in harsh environments like North Queensland and probably 85% of Western Australia. There are techniques that allow us to minimise these effects and afford better outcomes for lowering the potential for damaging ingress. In this application, which tests best reflect the forces involved in atmospheric conditions in all 4 seasons? In summer, the enclosure must endure cyclic temperature changes, high winds, possible high concentrations of dust particles, humidity change, solar infrared temperature contribution, and UV degradation over time. Flash thunderstorms where temperature change can be 20 degrees in an hour, along with heavy water inundation from 180-degree sphere, along with possible forces from below. In winter, possible freezing temperatures followed by wet, windy days, sometimes days on end. Do any of the laboratory tests accurately imitate actual conditions? So what normal situations can be considered untested for an enclosure? Water sitting on gaskets for long periods of time. Continuous rain inundation is unlike any of the tests. Submersion, maybe except for a few possible factors. Is the mounting surface completely flat with zero distortion? And over the inundation period, was there more than 5 degrees differential between the rain and the external ambient and the internals of the enclosure? Was there any guarantee that the gasket was free from any foreign material or damage during transit, fitting and subsequent use? AS NZS 3000 2018 mandates proper consideration of enclosures that house electrical devices. Clause 1.7.2 states that equipment must be protected against mechanical damage, as well as environmental impacts. It continues to mention condensation as an issue. It also mentions that the method of installation should not compromise the protection rating of the box or inbuilt methods of dealing with condensation. It also mentions additional equipment that may be used to improve performance in this area. Breathers or pressure valves can be installed, as well as special moisture drain fittings. The most important requirement is that any device that are fitted that require drilling, cable entries or HMI interfaces, etc., must be properly sealed in order to maintain the IP rating. It bears mentioning that the final IP rating of the installed enclosure is only as good as the most lowly IP rated device installed on the enclosure. A couple of useful tips to consider. Firstly, testing is specific. It's carried out in a laboratory. We cannot expect identical performance when we're using the enclosure in a different environment and an environment that is forever changing. Always mount enclosures on a flat surface. Enclosure wall distortion and breaching of the gaskets may cause issues. Never choose a higher IP rating that's necessary unless you weigh up all of the factors. The results may cause more problems than is absolutely necessary. Weigh up all the environmental and operational factors before choosing an enclosure or before choosing an IP rating. Always consider temperature differentials and solar radiation as factors. Solar radiation hitting your box can increase the temperature inside that enclosure by more than 15 degrees. So we need to take those considerations into account. Always consider additional ways of improving the performance of the bare enclosure. Things like shading it from solar radiation, having rain hoods fitted to the device, having breathing valves fitted to the device. These are always good fixes before you actually get to a problem. And always use appropriate glanding for cable entries and properly seal all mounting holes. In other areas, there's generally a packet inside each of the enclosures, especially in thermoplastic enclosures. These have got a couple of little plugs on them. These plugs are used to cover the screw holes that are used for mounting the enclosure onto a surface. Please use those plugs because that comes into the ability of the enclosure to meet its IP rating. Don't throw them out. Sometimes ingress cannot be prevented. Think of a way to avoid the ingress from doing harm or work out a way of clearing the ingress. So questions regarding this webinar may be directed via email to syoung@nhp.com.au or call NHP Customer Service Team on 1300 NHP NHP. Thank you for taking the time to watching, and we'll catch up on the next technical webinar.